Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very pleased to have Jiayin Dong with us. Hey, DJ, how are you today?
Yeah, I'm doing great. And thanks so much for inviting me for this series.
Oh, well, thank you so much for agreeing to talk about your really lovely APJ supplement article. I think it was really nice. So DJ, what's your geolocation? Where are you at?
Yeah, I'm at State College in Pennsylvania.
Okay. So you're a graduate student there?
Yeah, I'm a graduate student. Finish up my first year into beyond my fifth year this fall.
So you're in your fifth year?
Yeah.
Oh, okay. So you're going to be graduating this next year?
Yeah, hopefully, yes.
Cool. Well, Dr. DJ, I look forward to calling you that. That is awesome. Congratulations. And that, I think, is a really awesome board behind you there. I see lots of scribbles and Greek symbols and twiddle signs and lovely equations. You must be in a TA office or something, because that looks like a digital Ori off to your right shoulder, if I got the parity right.
Yeah, I think it's like a demonstration for transiting exoplanet. Yeah, there's a light bulb and the white ball going in front.
Yeah, very nice. Oh, okay. So it's specifically tuned for exoplanet transits.
Yeah, I think so. Yeah.
Okay. Very nice. Very cool. Have you ever used it?
No, I used something similar during the Astrofest, like the festival for public to learn about.
Oh, okay. Yeah. Well, I don't know if you did that in the past year. Probably not, given the
right. Yeah, last year.
Maybe this next coming year you'll get a chance to bring it out again. So I hope so. Very cool. So DJ, what do you like to do for research?
Yeah. So I'm interested in planet information. I'm doing numerical simulations and also using exoplanet observation data like TESS and transit and radial velocity data to study the formation and evolution of planetary systems. Yeah, that's mostly what I do. And cool. For this particular work, it's about TESS warm Jupiters.
Okay, awesome. And that is going to bring us to this very lovely APJ supplement article. Warm Jupiters and TESS full frame images, a catalog and observed eccentricity distribution for year one. And DJ, take us away.
Yeah. So it's my pleasure to talk to you about this work. As you can see, it's really a team effort. We have about 60 collaborators on this paper, and many of them are coming from the TESS follow-up groups, who are a bunch of observers who have been doing the follow-up observation of TESS planet candidates. And because of their contribution, we can validate these planet candidates, push them towards to be a real planet.
Cool.
And yeah, so if we go to the abstract, in this work, we focused on one type of exoplanet, what we call the warm Jupiters. And warm Jupiters are still close in giant planets, but they are having like an orbital period slightly longer than hot Jupiters. So yeah, here we are using like 8 to 200 days to define their orbital periods.
Okay.
And since it's a trended survey, we only observe the flux variation of the star during the planet's transits. So what we get is planet radius, not really the mass. What we use as a cat here is like 6 Earth radii as the planet radius cat. Yeah. Warm Jupiters is quite interesting. They draw less attention compared to the more popular hot Jupiters, but they're still like a very important component. It has a similar sort of origin channels compared to hot Jupiters, like how they formed, how they reached to their orbital configuration. So there are 3 major proposed origin channels: the in situ formation,
Okay.
the disk migration, and the high eccentricity tidal migration.
Okay.
Those are three major channels. And for each of those three channels, we have different expectations on the planet's orbital properties. For example, in situ, might expect the planet has a moderate or pretty low eccentricity. For planets formed via disk migration, we also expect sort of smooth dynamic back history for the planets. Therefore, also a low eccentricity orbit. And for the high eccentricity migration channel, on the opposite, we expect the planet to be on an extremely eccentric orbit before the planets get tidally circularized. So eccentricity is an important component, important information we need to know to tell what are those origins for these warm Jupiters. And so in this work, we use the TESS data, TESS full frame images, which is, so TESS is an all sky survey, has during its year one mission is basically pointing the southern ecliptic hemisphere.
Okay.
And it monitored like a fraction of skies for 27.4 days, just keep monitoring the fraction of the sky, and then rotate a little bit and rotate a little bit. And there are certain sectors, so certain sectors mostly cover the whole southern ecliptic hemisphere.
Nice. Nice.
Yeah. So using those full frame images data, we search for the warm Jupiter candidates. And so that will be like a huge amount of stars. So we need to do some like magnitude cut.
Right.
What we do is we cut the magnitude by TESS magnitude of 12.
Okay.
And yeah, so our survey is like a magnitude limited survey for warm Jupiters. And that will include 1 million stars already. And from this 1 million stars, we search the transit signals that qualified as a warm Jupiter candidate. And we found about 2,000 possible warm Jupiter candidates. Those are like threshold crossing events, not exactly like planet candidates yet.
Okay, good. I'm with you.
Yeah. So yeah, that's basically the 2.1 section. And 2.2 for those 2,000 threshold crossing events, we do a more careful search to remove false positives. Like some of them are just systematic, some of them are like single transit event.
Yeah.
Like yeah, we intentionally not include those since we don't know the order periods.
Okay.
And yeah, some of them are pretty obvious false positives, like eclipse binaries is the mean contamination of this catalog. So we do really careful selections to remove those false positives. And so yeah, with that, this whole more careful examination step, we end up with about 200 warm Jupiter candidates.
Okay.
Yeah, while we were doing the selection, the ground-based observers has already started their follow-up observations. And a fraction of our targets has been identified as false positives. And that's basically TESS has a large pixel, and that means usually a couple stars blended in the same couple of TESS pixels.
Right.
And even though we find some sort of trendy-like signal, and sometimes it's not from the target we are thinking of, it's like a background existing binary. That's like the major false positive scenario. And then the ground-based observer could like follow up those potential planet host stars and observe like whether the transit signal is on the target or is like off the target, is like background eclipse banner, since they have much better resolution.
Okay.
Yeah,
Cool.
so therefore we are able to identify a group of false positives, and those are listed in the table 1 of this paper. You can see like many of them are TOIs. Those are pushed out by the TESS team, and ground-based observers have been following up them since those TOIs has been published. And there are also a group of non-TOIs, like the last 10-ish tick IDs we listed here. Those are yield mostly from our survey, and then we send out a list of warm Jupiter candidates to the TFOP test follow-up group observers, and they're able to follow up on some of them and identify these false positives. Yeah, so that's quite nice.
Very good.
Yeah. So with our actually planet catalog, the next step we want to do is to better model these transit light curves. And what we used is so to fit the transit signals, we do a quadratic limb darkening model, transit model, plus a Gaussian process kernel to describe the variability of the photometric of the star.
Okay.
Section 3.1.
Uh-huh.
So the package I'm using is called Exoplanet. It's a pretty fantastic package developed by Dan from Mackie. Yeah, you heard that? So to slightly like reduce the computational effort, we didn't really directly model the eccentricity of the planet when we model the light curve.
Okay.
Yeah, so that's like a different part in our model. So when we model the light curve, we assume the planet has a circular orbit. And we mostly learn the transit eccentricity of the planet from its transit duration, and that is can be interpreted by the stellar density in the transit model. So it's basically if the planet has an eccentric orbit, then its velocity will have some sort of deviation from a circular orbit, and then the transit duration will be like either shorter or longer. And a shorter transit duration basically means a longer stellar density if they fitted with a circular orbit. So when we actually model the stellar density assumed circular orbit of the planet, the stellar density could be different from the true stellar density of the planet. So we compare those two values to, by the end, infer the eccentricity. This is a small trick we do to save some computational time, since we are actually modeling like about 200 planet candidates, and we are trying to do it in a feasible way.
Let me ask one question. When you say the stellar density, do you mean, what does that mean? Does that mean the radius of the star divided by the mass of the star divided by the radius cubed, or is that the number of stars in some volume, or what is that?
It means the physical density, like the mass of the star divided by the radius cube.
Got it. Okay.
It's especially if you rewrite the Kepler's law some way, you will get the transit.
You get an M over R.
Stellar density.
I'm with you. Yep. Good. Thank you.
So so this light curve model, we applied there another thing slightly different, which is we fit the transit by transit. What I mean by that is we fit the we like separate each transit and fit their individual mid-transit times. For example, this planet has 3 transits. We fit the first mid-transit time, second and third.
Okay.
And yeah, doing that allows us to figure out whether the system has any transit timing variation.
Yes.
Yeah.
Okay.
And yeah, I think that's mostly about what we do on the light curve modeling. Yeah, so table 3 has the priors we used.
Yes. Yeah. Okay. Very good. Yeah. Yeah.
Yeah.
Question is okay. Good.
Yeah.
Good. Gaussian process model. Okay. Good.
So yeah, after we feed light curves for this planning canvas, we did an analysis on the transit timing variation and the eccentricity inference. But like before that, I mentioned we have about 200 planning canvas. We have to remove about 100 of them just because their impact parameter are too high. So for Jupiter-sized planet, Jupiter is basically 0.1 of the solar radii. And that's the same for an impact parameter greater than 0.9. This is more like a grazing planet.
Right.
Or more unfortunately, it's just an eclipsing boundaries that are grazing. That's like another dominant false positives that we are trying to avoid.
Right.
So yeah, we have to remove another 100 candles because of their grazing light curves. Yeah.
Because they may not be what you think they are. Right.
Yeah.
Okay.
Yeah, so we did two post light curve analysis. One is the transit timing variation analysis. Just what I mentioned earlier, we fit mid transit time one by one, and then for each of these mid transit times, we fit a linear line. So yeah, it's basically the transit should appear periodically still, but they have a slightly variation if there is this transit timing variation.
Yes.
Yeah. So yeah, basically what we could learn is this residues, like the observed mid transit time minus the calculated mid transit time, which is just assume like perfectly periodic transit timing. Yeah.
Good.
Yeah. So yeah, that's the transit timing variation part. And a second analysis we did is this last paragraph before the section 4, which is to infer the planet's eccentricity from the transit duration. It has a fancy name called the photoeccentric effect. Yeah. Photo means like curve-ish, and eccentric means like you can infer the eccentricity of the planet from its transit like curve. Yeah.
Right.
Yeah. So yeah, we use the rho circ that are modeled from the light curves and compare this rho circ to the true stellar density that are coming from the isoconfig of the planet. And again, if those two values are very similar, then it basically indicates the planet is on a circular orbit. And if those values are really far away, like has a large ratio, then it more likely means the planet is on eccentric orbit.
Yeah.
Yeah. Okay. So yeah, that comes to our planet catalog. We eventually introduced a catalog of 55 planet candidates. Yeah, and yeah, that's also show in the figure 1. And what nice about figure 1 is that we actually show their wave band magnitude.
Yep.
Yeah, so we did the magnitude cut of those candles. Like when we search for these candles, we did the whole star magnitude cut at test band of 12, and that's also we did this cut also for a feasible ground-based follow-up. So you can see, yeah, the majority of our candidates are brighter than Vmag of 13, mostly brighter than Vmag of 12. And yeah, those targets are bright enough for like a 1.5 meter telescope to follow up, to do the continued follow up observation. Yeah.
Okay.
Yeah. So 55 candidates. That's the first part of this result. Yeah, it's also shown in the table 4. Yeah, you can see like we have many of the TOIs, and some of them have been confirmed already. Like those are, yeah, in the last column, I list, yeah, some of the published work.
Right.
A few are previously known planets. So, yeah, like VASP planet, VASP 162b, for example. Yeah. And also, there are a couple that are CTOIs already. This is by this work, Montalto,
Montalto is how I would say it. Yeah, Montalto.
Yeah, yeah, yeah. So, yeah, I want to highlight a little bit like for our non-TOI targets.
Okay.
Since we search the stars down to Tmag of 12, and the majority of TESS object of interest or TOIs are done by TESS magnitude of 10.5. So we have like 19 more candidates that were not TOIs before.
Okay, cool.
Yeah.
Yeah.
Yeah. But I think like for now, the new published TOIs do search deeper. So yes, many of them will be TOIs if they haven't yet been TOIs.
Okay.
Yeah. Yeah, I think that's mostly about table 4.
Good. Yeah. No, very detailed. It's nice.
And yeah, so we can look
Vision on those error bars. That's
Yeah.
pretty good. That's pretty good. Okay. Good.
Yeah, so this is the figure showing the trend timing variations. The y-axis is basically the observed mid-trend time minus the calculated mid-trend time. So yeah, those are transit timing variations you observed. And yeah, the first example is really nice one, the tick 5565 to 896. That's TOI 216 is a system that has been co-discovered by Becky Dawson and David Kipping.
Okay.
Yeah, it's a resonant pair of planets, so that's why you see this pretty huge transit timing variation signal. Yeah, like more than an hour. Yeah. Yeah, you see, I labeled those transit timing variations by slightly different colors and with their significance levels.
Right.
Yeah, this is criteria that indicates how strong this transit timing variation signal is.
Got it.
And yeah, it incorporates the difference, the variation you observed, and the uncertainty on mid-transit times. Yeah. So I would call like a greater than at least yeah, the 1 sigma detections or less, those 1 sigma H detections, I wouldn't say those are transit timing variation signals.
Right.
But some of them are actually like multi-planet systems. So we want to study the transit timing variation because if this planet warm Jupiter has companions, they are likely to be shown some level on their transit timings, on their transit timing signals. So this example tick 254 1133 11, like the second column, second to the last row.
Second column, second to the last row right here.
second columns, second to the last row, like,
Got it.
yeah, here, exactly, yeah.
Yep.
Yeah, this is actually a multi-planet system discovered by Chelsea Huang.
Okay.
And you see the transit timing variation for the warm Jupiter, which is shown in this black dots, is not really strong.
Yeah.
Yeah, so the hollow dots are for the inner planets, which is a 4-day planets not really included in our catalog.
Okay.
This the inner planets show like some sort of transit timing variation, but like the Jupiter doesn't really show that.
Yeah.
So this is really saying for many of these targets, we need a longer baseline observation to actually tell, to say, to be able to tell the companions from their transit timing variations.
Mm-hmm.
Yeah.
Mm-hmm.
Yes. Yeah, luckily, like majority of these targets will be observed again or has been observed already in the TESS extended mission. So we have at least double, or I guess no, sort of double the number of data points.
Okay.
Yeah.
Good. Cool.
Yeah. Yeah. So yeah, transit timing variation will be, it's important for us to know about companion properties if we don't observe them directly. But many of the candidates we found from year one, they couldn't really tell a strong story about their companions just from the 3 observations on their transit timing.
Right. Yeah.
Yeah.
Looks
Yeah.
like a money shot here.
Yeah. So yeah, from the rho star rho circ, we are able to infer the eccentricity of this planet.
Mm-hmm.
Yeah. And here is eccentricity versus orbital periods. You can see the majority of our candidates has an orbital periods less than 20-ish days. And the sort of expected, each test sector is 27.4 days.
Okay.
So if we only observe it by one sector, then we are limited by like 13.7 days to at most.
Okay.
Yeah, so those are like the cluster of those short orbital periods we find.
Mm-hmm.
And yeah, they're a lucky region, like those 2 test sectors overlapping between each other, and it means like the small fraction of sky being observed for 54 days.
Okay.
Yeah, and there are some even more lucky area, like there is a patch of sky called the continuum viewing zone, like during the whole year 1 mission, like that sector of the sky has been observed continuously.
Got it.
Yeah, yeah, but like those are small regions of the skies.
Mm-hmm. Yeah.
But yeah, we are able to find a few candidates from those really lucky zones. You can see on the x-axis, like we have about 10 quite long orbital periods, warm Jupiters.
Yeah.
Yeah. Yeah, this is the planetary space we really want to explore more. If TESS extended mission could help us a little bit more. Yeah.
So I think one thing that surprises me about this plot is most of them do not have a near zero eccentricity.
Yeah, exactly. Yeah.
10th is a pretty good eccentricity.
Yeah. So for those not circular ones, those are definitely not having a zero eccentricity.
Mm-hmm.
Yeah. For those low ones like 0.1, center at 0.1, their lower error bar still extends to 0. I think that's sort of the limitation, just learning eccentricity from light curves.
Yeah.
Yeah. So I would say like those bunch with median eccentricity near 2.1 or below 0.1, they are still consistent with the circular orbit.
Okay.
Yeah. Yeah, but like I totally agree. Many of them have non-zero eccentricities, and that might because why warm Jupiters are fun to study.
Yeah,
Yeah.
definitely. Very cool. Very nice. All right.
So yeah, this figure 4 is like replotting figure 3, but now the x-axis is semi-major axis.
Uh-huh.
Yeah, and I'm adding a few lines to like sort of helping people to understand what are possible
Okay.
yeah formation pathways for this warm Jupiters. Yeah, so I mentioned before we have three proposed origin channels for warm Jupiters.
Uh-huh.
And particularly for the high eccentricity had a migration origin. Those warm Jupiters begin as cold Jupiters, and yeah, they have some dynamical interaction by nearby planets or nearby stellar companions that excite their eccentricity to some extreme value. And then they are getting tidal dissipation and losing orbital energy, and during this process, their angular momentum kept roughly the same.
Okay.
So yeah, that means when they are losing orbital energy, their semi-major axis gets smaller, but they keep their angular momentum, so their orbit is getting more and more circular.
Okay.
Yeah,
Mhm.
and that's exactly what I'm showing on this black dash line. Yeah, exactly.
Yep.
So it's like a constant angular momentum track.
Right. Right. Yes.
Yeah.
Mhm.
Yeah. So we expect a cold warm Jupiter follow this track and getting inwards to become like some as a warm Jupiter still on a super eccentric orbit, or like a circularized hot warm Jupiter-ish
Mhm.
planet. Yeah. So you can see a couple of targets are actually on or above this black dash line, and those are pretty likely to be planets that are undergoing high eccentricity migration,
Okay.
which is pretty cool. Like we are catching those planets.
Yes. Yes. In the axis peaks.
Yeah,
Not
yeah.
a long phase.
Yeah.
Nice.
I want to highlight one, which is this the highest eccentricity one we have. Yeah, this orange star. Yeah, it's TOI 3362b,
Ooh.
and we are able to confirm this planet
Okay.
and also confirm this extreme eccentricity. It turns out to be 0.82, 0.816. That's the
Okay.
inferred value of this planet. Yeah, so yeah, it's pretty nice to know like those warm future candidates that are likely to be undergoing highest interest in migration are actually planets, not really some false positives.
Mm-hmm.
Yeah,
Mm-hmm.
and yeah, this is the high interest migration channel, and we have two other proposed channels for warm Jupiters. One is in situ formation, and for in situ formation, we usually expect like multiple giant planets formed, and those giant planets will have like gravitational interaction.
Mm-hmm.
Yeah, and excite the eccentricity somehow. Yeah, and that's this dash delta line. We are labeling here. Yeah, planet-planet scheduling line. And so we have some sort of theoretical estimation on the maximum eccentricity this planet could reach by the planet-planet scheduling. When it's getting higher to this value, it's more likely to lead to the collision.
Mm. Mm. Yeah. Okay.
Yeah. So
Okay. Mm-hmm.
yeah, so you see like many of these warm Jupiters are close or below this line. So that's nice. And for the last of the three proposed yeah, I think, yeah, so you're like clicking on this region between those two lines. How do we explain those?
Yeah. One of
Yeah.
the.
Yeah, so yeah, our understanding on those planets in between those lines just could have, so we are like observing them at a snapshot.
Yes.
And that is saying these planets could have eccentricity perturbations, like they have some, like for secular interactions, like those planets have companions or outer planets in the system that are still interact with them. Then their eccentricity is centered at some value, but could also get lower beyond and lower this value. It oscillates between some range. So we are like observing them at a snapshot.
Okay.
And then like, yeah, if they have an outer companion that has been, these two planets are interacting, then we may expect those planets between those two lines, like either going higher or below, to follow one of the origin channels for this one. Yeah, that's our explanation so far.
I understand. Very good. It's very cool. Very nice. All right. Awesome. Okay, and then you said there were three. So
yeah. So the last one is the disk migration, and for this migration is like those still those giant planets begin as a called Jupiter with a larger semi-major axis, and then when they're still in the protoplanetary disk, the torque applied on the planets migration inward, like the type 2 migration. People are talking about like the planets open a gap and migrating inwards. In that case, basically expect low eccentricity, but there are also some recent work saying from their numerical simulations showing like the planet could still get some sort of non-circular orbit, but not like to some extreme values, like it couldn't really get to like 0.6, 0.8, like some of the planets we observed.
Right.
Yeah. This eccentricity versus major axis.
Okay.
And yeah, we also like look briefly into eccentricity versus the sizes. Yeah, nothing so conclusive we can reach here yet. But it's quite interesting to see like the majority of the super eccentric or highly eccentric warm Jupiters we have only sizes between like 8 to like 13 Earth radii.
Right. Right.
Yeah, we couldn't tell too much about this yet. It's like a nice trend we observed. We're showing it here. We have like a short discussion on what could possibly be happening. Nothing too conclusive yet.
Okay. We'll come back to that then. Okay.
Yeah. So yeah, that's mostly about the catalog. And so since we have the we could infer the planet eccentricity from their like row star and row circ, and we have a catalog. So we think, why don't we calculate the eccentricity distribution of this catalog? Yeah, since by the end we want to learn the warm Jupiters as a population. Learning them like one by one, it could tell a lot about their own dynamical history. But learning them a population, we can like more generally saying how warm Jupiters form. And yeah, so the technique we are using here is called the hierarchical Bayesian modeling. Yeah, it's a fancy word, but it's basically just for each individual warm Jupiters, we can infer its own eccentricity. Now we have 55 of them. Let's put it all together and use some distribution to describe their eccentricity distribution.
Yes.
And yeah, let's infer those hyperparameters, which are those parameters that describe the eccentricity distribution.
Okay.
Yeah. Yeah. So here, figure 6 is just the graphic model of the hierarchical model. We are using basically parameters in the bar in this plate are the parameters for each individual worm Jupiters.
Mm-hmm.
Yeah, you can see this rho star for each planet from the isochrone fitting. It follows some probability density distribution, like yeah, and yeah. So for example, like we know this planets we calculate from their isochrone fitting. We know is like 1 gram per centimeter cube plus minus 1.1. So that's like some sort of distribution. And eccentricity is basically yeah, the second term eccentricity is basically a flight prior, like some value between 0 to 1, and it's informative. And so that's this omega. Omega is argument of periapse. So to describe an eccentric orbit, we need those two values. And yeah, so basically using this rho star eccentricity and argument of periapse, there is a directly functional form to calculate the rho circ. And this rho circ can be compared to the observed rho circ that we are inferred from the light curve. Yeah, so yeah, again, if the probability density distribution we have on rho star is very different from the rho circ, then the planet is likely to be an eccentric orbit. Yeah, and there is one last component, which is this what I call the OBS observed. That's where the part where we take account of the transit probability. So yeah, the idea is the planet has a higher transit probability when, so let's say a planet has an eccentric orbit, and then the planet has a higher chance to transit when its argumental periapse is aligned to us. Yeah, so yeah, that's the part we take account of this transit probability effect. Yeah. Yeah, so inside the plate has the parameters for each individual planets, and then outside the plate there are hyperparameters for the eccentricity distribution. So for a beta distribution, it has 2 free parameters, and for the most from the posterior of those 2 impact parameters. Now impact from the posterior of those 2 hyperparameters, we can construct the eccentricity distribution. Right. Yep. And this leads to the figure. Let's go down a little bit.
Or distributions or mixture models.
Yeah, those are.
Yep.
Yeah. This figure 7. So yeah, the upper green one is for it's a eccentricity distribution we inferred using this beta distribution as a functional form. Yeah, it's like what we see from the eccentricity versus image axis plot before. We already know like worm Jupiters, many of them have non-circular orbit. And this eccentricity distribution is reaffirming that. It has just eccentricity distribution has a peak like near 0.25-ish. Yeah, like one peak is like 0.2.
There's lots of curves with capacity, and so that's the total number of distributions from which you then derive the big thick green line.
Yeah, so yeah, the big thick green line is like the median of these hyperparameters, like how does the distribution looks like.
Got it.
And the lighter, shallower green lines are like draws using the hyperparameter draws from the posterior. We derive like other format of the distribution.
That's right.
Yeah. So yeah, overall, if you look at this, it's still pretty much constrained. Yeah, for beta distribution, it has a quite flexible format. So it could has this bell shape. It could also has a high spike towards zero. So yeah, you see a few divergence draws that having a shape like that.
Right.
But our best model distribution gives this nice bell shape. Yeah. Yeah. So it's slightly nicer to view this as the relay distribution. Yeah, it has in general it has a shape similar to this beta distribution. But you can see its draws, since it only has one free parameter, it is much more tightly constrained. And from its draws, we see this nice bell shape. Yeah. So yeah, the idea is for beta and relay, those are really nice distributions that has been used in many studies. They're like a single component model. And what we think about worm Jupiters are that they could have those low eccentricity. They could have those origins gives low eccentricity or moderately eccentricity solutions, but they also have those like high eccentricity migration origin channel that gives extreme eccentricities. Yeah, so that's motivate us to use a multi-component distribution. Yeah, so yeah, we are thinking of to separate this like this bell shape from the beta and relay, really wide width of this distribution into multiple components.
Okay.
And that's why we start this mixture distribution idea. And this mixture model is like a really flexible model. We basically do two Gaussian components. Like it could have two bell shapes, but the model is flexible to become a single component model if it preferred for that. So if our data is truly a single component data, then you will just see the bell shape has the relay or beta.
Right.
That's a flexibility we gave to this mixture model, and the best constraint one we find it's actually in fact two components. And it demonstrate one component about 50% of this worm Jupiters fall into the low eccentricity distribution, and 50 goes to this high eccentricity component. I think that's a really fun distribution that we can borrow for future theoretical studies. Worm Jupiters are unlikely to be a single component population.
Several of those three channels contribute.
Exactly.
Yep. Absolutely. Very cool. All right.
I also want to say so far we are doing this using the catalog of planet candidates, and we haven't yet do like corrections for the detection efficiency or like the baseline age correction, because like some of them have long work, some of the planets have long orbital periods, some of them have short orbital periods. So I would say this is a first step, an overview on this planet candidates, and we need to do like further more detailed work. So first of all, the TESS extended mission is happening right now. I think it's just finishing up his TESS just finished up his third year of observation. So this year one sky area being observed again over the past year. We expect to detect more planets like those single transit event in year one. It may has another single transit event in year three, and that will be pretty cool to discover more of this long orbital periods planets. Like I was showing, we have most of them less than 20 days. We want more beyond that.
Yeah.
And as mentioned, the TTV we find from this planet candidates are mostly tentative because we only have 3 transits. And from the using the year 3 data, we could probably tell more.
Cross fingers.
Yeah. And I think what's even more important to do is to follow up these planet candidates. And I want to I really appreciate the effort from the TESS follow-up group observers. So for our 55 candidates, we have now mostly validated all of them, and 42 out of the 55 are validated planets.
Okay, nice, good.
Yeah, this also means like some of our results we get earlier, for example, the eccentricity distribution is not too contaminated by the false positives.
Okay.
So yeah, that's pretty nice.
Mm-hmm.
And yeah, I in this follow-up observation paragraph, I also discussed like what are some planets we want to like pre-authorized, and does include this 464300749, which is TOI 3362b. We just submit this a confirmation paper on this target.
Oh, good. Okay.
Pretty cool. And yeah, so with this validated catalog of warm Jupiters, we hope to do more better work that help future directional modeling on warm Jupiters, like to infer the intrinsic eccentricity distribution and to even figure out the occurrence rates of warm Jupiters. Since we have this many of stars and we expect this many of them transiting and we find this many. So yeah, it will be nice to do these sort of statistical work too.
Indeed. Very good.
I think that's mostly it. That's all the material, most of the majority of the material contained in this work.
Okay.
Yeah, you can see from the acknowledgement, like this is a huge team effort. Yeah, it's also my first time to coordinate with this many people, and
That was fun.
yeah, it's a different experience. Yeah.
Indeed.
Yep. Yeah, but like to be able to get this planets validated this quick, it's all about this follow-up group observers. Without them, we won't be able to do that this quick. Yeah.
Very good. DJ, I want to thank you so much for walking us through this very lovely APJ-SUP article on warm Jupiters. So you touched on it a couple of times on where do we go, let's say, over the next 5 years. You mentioned, TESS 3 data coming, some follow-up.
Yeah.
Will there be maybe other interesting stuff, like let's say from Plato, or are there additional theoretical calculations one could do to determine some of the properties, the eccentricity of these warm Jupiters, or how many warm Jupiters there are, that kind of stuff. So kind of give it a future look, and where do we go beside your PhD thesis, over the next few years?
Yeah, yeah. Yeah, I think the whole warm Jupiter area is super exciting because of these missions, TESS extend mission or Plato or future. There is a successor of Kepler mission going on in China right now. Like
Yeah.
we may plan to like revisit the Kepler field for another 4 years. Yeah, I think those will, the surveys will help to boost the warm Jupiter sample a lot. And with a survey like TESS, we are doing those where we could search warm Jupiters around those bright stars that allow a detailed follow-up observation.
Mm-hmm.
We need to study them more carefully to know like what happens to them exactly, not just really a rough saying like this could be this or that.
Okay, fair enough.
Yeah.
Yes, yes, very good.
Yeah. Yeah, I think that's one important point, like a more detailed follow-up observation. And a second part I'm super excited about, like many of these TESS warm Jupiters has been observed with nearby companions.
Okay.
There are systems like TOI 216, TOI 1130, and there are more that are like, yeah, people have been drafting some more work on also warm Jupiters with companions that I may not yet supposed to tell their names yet. Yeah.
You'll
Yeah, I think,
you have to watch for those future papers, people.
yeah, exactly. Yeah. Yeah, I think companions is another direction that could tell a lot about this warm Jupiter origins. For the high eccentricity migration, we don't expect them to have nearby companions since their eccentricity is too extreme. It's likely to just get nearby companions scattered away. But for the in-situ and disk migration, they may have nearby companions.
Yeah.
And we have different expectations on the properties of nearby companions for the in-situ and disk migration channel.
Right.
I think, yeah, that will be a quite exciting part of the structural work we can do.
Very nice. Cool.
And yeah, overall on warm Jupiters, it seems pretty likely to me that warm Jupiters have a mixture of origin channels.
Yes.
And from the high, like eccentricity is a key to tell the fraction of the systems that are coming from the high eccentricity migration. So we have, if we like have the predict number of these warm Jupiters with extreme eccentricities, and we have the observed number, then we can get the fraction. Yeah, like what fraction of the warm Jupiters that are coming from the high eccentricity migration. That's like the number we can constrain.
Nice.
And then for the rest two channels, the companions will tell a lot.
Yeah.
So yeah, just like yeah, the picture I'm really interested to figure out too. Those three channels are yeah, like knowing one better, also ruling out the other two. Yeah, so yeah, I feel like the field will have lots of advances in the next couple of years too, given those.
I predict a very interesting PhD thesis and follow-on work as a postdoc on this. So it'll be really cool. Very nice. DJ, thank you once again. And thank you everyone for listening in. I hope this makes your astronomy day just a little bit brighter and better. And we'll see you on the next one. Thank you. Bye-bye.